This video will cover sections 1.13 and 1.14. 1.13 introduces some algebraic terminology. So we're going to take a look at algebra, which is a branch of math in which the variables are used to represent numbers and numerical operations are generalized. A constant is a value that doesn't change. A term is a constant or a variable or a product or quotient of constants and variables. There are some examples here. An expression is a phrase that contains one term or more than one term. Here's an example. An equation has an equal sign. And it's helpful to think of an expression as a phrase and equation as a complete sentence. Also, we simplify expressions, but we solve equations. So consider this expression, 3x minus 12y. There are two terms separated by a subtraction sign. The constant 3 and the variable x are multiplied, which makes them factors of the term 3x. Likewise, the constant 12 and the variable y are being multiplied, which makes them factors of the term 12y. Identify all the components of this equation. So we notice how the variables and constants are connected. We can identify the operations being used. So if you notice here, here's a term, and we have a negative x and a negative 8 and an x, which forms that term, plus 1, which is another term, 2x is another term, and 6 is another term. And again, the factors here would be negative 8 and x, 2 and x. The variables are x in this particular equation, and it has four constants, negative 8, 1, 2, and 6. The term negative 8, remember we just said on the prior slide, has factors of negative 8 and x. The term 2x has factors of 2 and x. And again, there are constant terms 1 and 6. Identifying factors and terms can help us with fraction operations. We know that to simplify a fraction, we divide both numerator and denominator by a common factor. Thinking of this process as division instead of canceling, which is not a defined operation, makes it clear whether there's a 0 or a 1 left. If possible, simplify before performing the operation in each part. So if you notice here, we could just go ahead and multiply, which would give us 12 over 36, but we notice here that we could have simplified by canceling out or dividing both the numerator and denominator by 4 in order to get the final answer. Actually, we could also do here, 3 goes into 9 3 times, which would have led us right to 1 over 3. 4 ninths divided by 3/4, we need to change this to multiplication, so 4 ninths times 4/3. Nothing we can really simplify here, so we just multiply the numerator and multiply the denominator. Here, we're just going to add in the numerator and add in the denominator. We're not adding two fractions, we're simplifying the numerator and denominator individually. Recall that exponents can be used to express repeated multiplication. So for instance, instead of writing 2 times 2 times 2 times 2, we can write 2 to the 4th. The factor that's being repeated is 2, and the number of factors is 4. In this particular example, we call 2 the base, and 4 is the exponent. A polynomial is an expression that has one or more terms that are constants or products of variables and constants, and we have special types of polynomials. A monomial has one term, a binomial has two terms, and a trinomial has 3 terms. Here are some examples. This is a polynomial, it's also a trinomial. The degree of a polynomial in one variable is the highest exponent that appears on that variable in the polynomial. I'm going to go back just for a minute here. In a polynomial, the exponent must be a whole number. So the polynomial here, 4x squared plus 3x plus 5, is a trinomial, has one variable. The degree is going to be degree 2. If the expression is a polynomial, identify it as a monomial, binomial, trinomial, or none, and then identify the degree. If it's not a polynomial, state why and give a reason why. Okay, so we see two terms here. It is a polynomial, single variable, so it's going to be a binomial, and the degree is 2. This has 3 terms, so it's a trinomial, and the degree again is 2. This is a monomial, and its degree is actually 0 because there is no exponent. basically it would be x to the 0, which is 1. This is not a monomial, binomial, or trinomial. It's a polynomial, and the degree here is 3. This is not a polynomial, and because the exponent is not an integer. And this is a monomial in f with a degree 3. Here we have another binomial, and in this case the degree is 4. And this last example is not a polynomial because the variable is not in the numerator, it's in the denominator. In section 1.4, we're going to learn about generalizing patterns. So consider this sequence, 2, negative 4, and we want to fill in the next 3 numbers. I could say, well, I'm multiplying by negative 2 each time, so the next number might be 8, and then negative 16, and then 32. I could also be adding, or subtracting a number. I could also just be alternating 2, negative 4, 2, negative 4. So you can come up with 3 different rules here as you work on this example in your book. So we often need to look at a list of numbers and make a guess about the pattern that exists. This will help us when we create models, graphs, and projections for the future. The process of making an educated guess or conclusion is based on the evidence provided, and it's known as forming a conjecture. You will need to make a conjecture in some of the problems in this section in order to come up with the terms in the sequence. So for instance, here's an example. The Fibonacci sequence is a sequence of numbers that follows an interesting pattern. Write the next 6 numbers and try to figure out the rule that helps you to generate that particular values. So if we look at the pattern that we see here, we see 1 and 1, and then we see a 2, and we notice that 2 is the sum of 1 plus 1, and then 3 is the sum of the prior 2 numbers, 5 is the sum of the prior 2 numbers, so we can continue and fill in here with an 8 and a 13 and a 21 and so forth. So when we talk about reasoning, we have inductive and deductive reasoning. In both kinds of reasoning we use in everyday life. Inductive is where we form hypotheses or conjectures, and deductive is used to prove conjectures. So in deductive reasoning, we go from a general to a specific. In inductive reasoning, we go from the specific to the general. And we only need one conjecture in order to show that a hypothesis is not correct. So let's say a student knows that a number is even if the last digit in the number is even. So when the number 12 is even, 14, we know that's true. The student wonders if a number must be divisible by 3 if the last digit is divisible by 3. Find a counterexample that proves her conjecture is false. So the student's conjecture is that if the last digit is divisible by 3, then the number is also divisible by 3. So a counterexample would be a number with the last digit that is divisible by 3, but itself is not divisible by 3. So let's try the number 13. It ends in a 3, but the number 13 is not divisible by 3, so therefore this is a counterexample. There are many others, but you only need one in order to show that a hypothesis or a conjecture is not true. So that last number is a digit that's divisible by 3, but the number itself is not. So we don't get a whole number answer when we divide 13 by 3, so 13 serves as a counterexample. So consider this sequence. Describe how each term is generated from the prior term. So if we take a look at that sequence, what do we see is happening? Looks like it's being divided in half each time. So 100 divided by 2 gives me 50, divided by 2 gives me 12, divided by 2 gives me 12.5. Each number is half of the previous number. And then a couple examples from your book on page 121. So what is the pattern in each sequence, and find the next 2 terms. So what do we see happening here? How do we get from 5 to 17? Looks like we add 12. Do we add 12 here? Yes. Do we add 12 here? Yes. So the next 2 would be 41 plus 12 is 53, plus 12 again is 65. Look at the second example. Here it looks like we're subtracting, let's see, we're subtracting 4, 4, 4. So the next 2 numbers in the sequence would be 2 and then negative 2. The third sequence is a little more complicated. We don't really see a pattern going on from number to number, but if I look on every other one, I notice a pattern. 9, negative 9, negative 8, negative 7, so I would hypothesize the next number here would be negative 6. And then look at the alternate ones, 4, 5, 6, So I would hypothesize a 7. So the next two would be negative 6, comma 7. And then finally this sequence here, 3x, 4x plus 1, 5x plus 2, 6x plus 3. So the x terms are going up by 1x each time, and then we're adding. So this would have been plus 0, plus 1, plus 2, plus 3. So the next term here would be 7x plus 4. So hopefully this will help you as you're working through the problems in sections 1.13 and 1.14.